We present a framework to synthesize human motion from object motion. Given a sequence of object states, we generate full-body human motions interacting with the object using a two-stage conditional diffusion model. We train the model on our collective dataset with 10 hours of human-object interaction motions. With the learned model, we develop a novel system that captures full-body human manipulation motions by simply attaching a smartphone to the object.
I've had enough of this stupid suit.
What happened, Master?
I can't accept that every time I catch a criminal, I have to ensure these anti-human designs. Who thought of putting wires in my clothes?
I'm sorry, young Master, but your over 100 black techniques require circuit transmission.
Don't worry, let me show you this.
Input the electronics position and a library of machine data, which you are expected to perform, and you can get the best wire design that meets your needs.
Thank you.
In this paper, we proposed a common-sense knowledge-driven joint reasoning approach for object retrieval based on the contexts. We proposed an SHAOG to model common-sense knowledge, including the background, the human, non-interactive object, and interactive object. Based on the joint reasoning approach, we proposed an object retrieval system.
Thank you.
I'm so stressed about the fast forward, I have no idea what to show.
Wait a second, maybe you should try some occupational therapy to calm yourself down. Have you tried smoking?
Smoking? But I hate the smell, and it does not sound so good for my health.
Not smoking. I said smoking, with a needle, not a cigarette. Smoking is an embroidery technique where multiple points on the fabric are stitched together, creating pleasing geometric textures.
That's so pretty, but it takes ages to fabricate it. I don't have so much time.
No worries, you can use our algorithm to have a virtual therapy in no time. Come to our presentation for more details.
Thank you. To see the result, come to our talk tomorrow.
We introduced SolFormer for sewing pattern reconstruction from a single image. Our sewing pattern allows for flexible garment manipulation, including texture and human shape and pose. We also present Sew Factory, a dataset comprising 1 million image and sewing pattern pairs. Our garment reconstruction allows for human animation in a physically plausible manner, enabling garment to move seamlessly and naturally in accordance with human body movement. Thank you.
Lego is fun. When you have artistic logos and clip art designs, do you want to use Lego pieces to reproduce them physically? We provide the first solution. by focusing on the edge boundaries and formulating a graph optimization framework. We efficiently solve this Lego tiling problem and generate a Lego sketch model. Particularly, our method considers non-rectangular Lego pieces, hence can reproduce smooth boundaries and preserve sharp features. What's more, we can arrange colorful pieces over multiple layers. To know more, please come to our talk.
Thank you.
Conventional holographic displays use a field sequential color approach, rapidly displaying monochromatic images in succession. The human visual system merges these images into full-color images. We introduce a new technique in computer-generated holography named multicolor holograms. We optimize phase patterns that can be illuminated by multiple color primaries with varying light intensities. Our method enhances image brightness without any hardware modification. For in-depth technical details, please consult our technical presentation.
Thanks to its ability to solve the variance accommodation conflict, holography is a promising display technology for augmented reality glasses. However, to design a wearable holographic AR headset, several challenges need to be tackled, such as the real-time calculation and display of full-color binocular holograms and the reduction of speckle noise in the reconstructed images. While solutions have been proposed to tackle each of these challenges independently, in this work we combine these components into the first fully integrated holographic AR headset with embedded hardware hologram calculation. If you want to learn more about our work, please come to my talk.
Thank you.
Traditional holographic displays rely on field sequential illumination, meaning that a unique SLM pattern is displayed for each color channel. The persistence of vision causes these three frames to be perceived as a single full-color image. Unfortunately, this approach reduces the effective frame rate of the display by a factor of 3, leading to distracting artifacts such as judder and color separation. We propose a simultaneous color holographic display to eliminate these artifacts. Our proposed method introduces no additional optical elements. Rather, it relies on an extended phase SLM and a perceptual loss function to solve the now ill-posed SLM optimization problem. Our method enables the display of both 2D images and 3D scenes from a single RGB illumination. Come join our talk to hear more about this.
Conventional holography using a single SLM still suffers from speckle noise. To reduce the speckle, we leverage polarization channel by integrating a halfway plate and a meta surface. This array of nanostructures allows uncorrelated phase modulation in orthogonal polarization states. Therefore, reconstructed image shows different speckle patterns depending on the polarization states, and these can be incoherently summed to reduce speckle noise. A regionally optimized meta surface demonstrates improved image quality and reduced speckle noise. Thank you.
Holographic displays shape incoming light so it looks like it came from a real three-dimensional object. However, the laser illumination in these systems results in speckle, which is a pattern of dark and bright spots caused by interference. Speckle makes the displayed image noisy and visually unappealing. We propose a speckle reduction technique using multiple sources of illumination. Each source creates a unique speckle pattern, and these get superimposed and averaged at the eye, suppressing speckle. We use two modulators to enable independent control of each source, which allows us to create arbitrary image content. Our method can substantially reduce speckle on both 2D scenes like this, and on focal stacks with natural defocus blur.
See you there.
Creating photorealistic 3D avatars typically involves computationally expensive surface tracking, and it remains challenging to obtain relightable appearance. In this work, we propose Travatar, a novel framework for capturing and reconstructing high-fidelity relightable 3D avatars without explicit surface tracking. Our Travatar is trained with dynamic image sequences captured in a light stage under varying lighting conditions. Our method enables realistic relighting under illuminations of arbitrary environment maps. In addition, our reconstructed avatars can be animated and rendered in real time.
Thank you.
Neural surface representation like I am avatar produces good geometry but takes time to learn. Instant volumetric methods like Insta converges in 10 minutes but produces noisy geometry. Our method Flare learns a canonical deformable mesh representation in just 15 minutes and produces a good quality surface. Additionally, our neural approximation of the illumination combined with physically based rendering allows our avatars to be real. Come to our talk to learn more. Thank you.
We propose Sailor, a novel method for human free-view rendering and reconstruction from very sparse RGBD streams.
The inputs for each frame are raw RGBD images from 4 fixed views. We denoise raw depth maps and obtain the fused points cloud. Then, we build the 2-layer tree from the obtained BSDF volume.
We perform ray voxel intersection and sample points. Our SRONet predicts color and occupancy for each point. Finally, we obtain the 3D mesh and rendering results. Here, we show some of our live full body and portrait rendering. Thank you for watching, and welcome to our talk.
Thank you.
We present photorealistic full-body avatars that can be driven by sparse RGBD views, body pose, and facial key points. It can reproduce the appearance and dynamics of challenging clothing that closely match the input views. Our models are trained in a multi-view capture system, but they can be taken to a different testing environment and be directly driven by 3 Kinect sensors to track the closed body motion with original appearance. Alternatively, they can be fine-tuned and adapt to the new illumination and recent body change. Thank you.
We proposed a novel method for closed human modeling from sparse RGB images. Despite the impressive result by employing implicit function-based representation, we revisit volumetric representation and prove that better performance can be achieved with proper system design. The result shows the robustness of our method when handling complex geometry and multi-person. Please come to our talk for more details. Thank you.
The emergence of neural field as a data representation has paved the way for applications in visual computing and beyond. Neural fields are typically evaluated via point sampling. For our goal, however, we require the continuous aggregation of values. Using convolution identities, we are able to reduce this continuous operation into a sparse sum product. Moreover, we show applications such as motion blur synthesis, image filtering, geometry filtering, and more. Consider coming to our talk.
The performance of neural radiance fields degrades significantly when only a few input images are available. We find that the high capability of the nerve leads to overfitting to the sparse training views. Specifically, positional encoding and view-dependent radiance lead to floaters and shape radiance ambiguity respectively. By employing helper models that learn only simpler solutions, we guide the nerve to choose simpler solutions wherever possible and mitigate the distortions. We achieve very good view synthesis performance with as little as 2 input views and outperform all the existing models in the sparse input setting.
I am no magician, all secrets will be revealed.
We propose Dream Editor, which allows users to use text prompts to edit a neural field scene. Dream Editor generates precise and high-quality editing results while maintains irrelevant regions unchanged. We first distill a mesh-based neural field from the original sense, which enables us to achieve selective editing. Then we use the cross-attention maps from T2I model to locate the editing area in the mesh according to the keyword. Finally, we edit the target object in the neural field under the control of text prompts through the T2I diffusion model. Experiments show that Dream Editor can perform accurately editing according to the text while ensuring consistency in irrelevant areas.
Thank you.
GAN-NERV takes advantage of generative adversarial networks to recover high-quality neural radiance fields in challenging real-world scenarios. Even with careful scene capture, prior NERV approaches tend to produce blurry results due to ambiguities. Our patch discriminator approach introduces additional constraints, which leads to sharper results, especially in areas with insufficient view coverage. Join our talk tomorrow afternoon.
Accurate camera poses, as any errors can lead to subpar quality as shown here. By jointly optimizing the camera poses with the NERF, we get better quality reconstructions even from noisy input cameras. Current methods in camera optimization overlook the fact that certain parameters influence rendering more than others. We present a method to automatically precondition cameras to normalize their effects. Our preconditioning technique allows cameras to converge to the right solution where previous methods fail. Our method, called CAMP, delivers high-quality view synthesis results even with low-quality camera inputs. Come see our talk on Wednesday.
A subdivision surface is produced by recursive refinement of an input mesh to get a series of refined meshes that converge to a smooth limit surface. The subdivision process defines 3 types of vertices in the refined mesh, each of which corresponds to a specific rule for vertex computation. These subdivision coefficients can be tuned for different target applications. We present a continuous family of tuned subdivision schemes that are unified under a single intuitive parameter lambda. By proper selection of lambda, the resulting subdivision scheme can be better suited for various applications, such as modeling, graphics, and engineering analysis. For more details, please join our talk.
Thank you.
Here is an interesting observation. If we have sample and SVG in place, then simplify back, we are supposed to find the exact same solution as the input. But in fact, all of the vector graphic editing softwares produce noticeable error in this easy task. Inspired by mesh simplification method, we propose a new algorithm for simplifying Bezier splines while maintaining high fidelity. We are sure to find the smallest possible zero-error representation first, then move on to the subsequent lossy simplification. Our method can be extended to higher dimension. Go to our session tomorrow afternoon to find out how to compress your SVG animation without loss of quality. Thank you.
For the modeling of planar curves, methods such as kappa curves that place control points and salient features have become a tool of choice. We present K-surfaces, a generalization of this approach to surfaces. For 2 parametric dimensions, this becomes more challenging since there may be multiple solutions with curvature extrema at the same location, and G1 continuity is generally too restrictive for quadratic Bezier networks. We show that a neural network can predict a consistent surface solution and address the continuity problems at patch boundaries using subdivision surveys. Interpolation and continuity conditions are maintained in interactive rates, providing an intuitive modeling tool. We are looking forward to discuss with you after our talk.
B-spline surface intersection is a fundamental task in computer-aided design and geometric modeling systems. In our algorithm, after fast collision detection using oriented bounding box, we then implicitize one of the parametric surface. Topology determination is then executed to find the critical points and boundary points. Then, we compute the intersection curve in 3D space and clip it to add up the parametric domain. Our algorithm well treats all types of intersection topology with practical efficiency, including cross-singularities, tangent points, boundary intersections, tangent curves, high-order contacts, as well as several isolated singular contacts. Welcome to our talk.
Thank you.
We present a work to build a fully edible digital scene from a single photo. Our pipeline used learning priors to generate a coarse scene. Then we use differentiable rendering to refine the scene. If you want to learn more in detail how we translate a single photo to a fully edible scene, come to our talk.
Thank you.
In inverse rendering, we optimize scene parameters to fit a reference image using gradient descent. Unfortunately, gradient estimation can come with much Monte Carlo noise, slowing optimization. As we adjust parameters in each iteration, the gradients change only slightly. We reuse sparse gradient samples by estimating this slight change with a small variance, greatly speeding up convergence. Join our talk to find out more.
Thank you.
Physically-based sequence rendering can recover object geometry from field shots because it can understand indirect information like shadows and interreflections. In this paper, we introduce an impressively simple formula of the boundary derivatives for not only meshes but also a variety of shapes. We also propose a new projective sampling strategy that can compute high-quality gradients magnitudes faster than before. This allows us to recover the shape of this chair from one single reference image. Thank you.
Robustness and generality are two challenges for current physically based differentiable rendering methods. For example, we want to recover the position of multiple objects observed through reflection and refraction. Existing differentiable rendering methods often get stuck in local minima or fail to converge. We propose the extended path space manifolds. It constrains light path geometry by scene parameters, thus we can compute gradients of light path. Combined with optimal transport-based loss function, we succeed in this case and many other types of scene like shadow scene, caustic scene, and glossy scene. Please come to our presentation for details.
Thank you.
Differentiable rendering enables gradients to propagate from images to objects through the rendering equation. But object deformation requires evaluating a complex boundary integral over the visibility silhouette. Some methods have been proposed. Warp-pair sampling transforms such integrals into interior ones, enabling the use of an old-school interior integrator. Meanwhile, PSDR starts by sampling a boundary array and uses path space formulation, allowing advanced path sampling. Imagine combining their powers. Our method rewrites warp-pair sampling in path space to harness the strength of both methodologies. This novel formulation not only enhances our capability to handle intricate scenes, but also elevates the efficiency of the optimization process.
Thank you. Look at this video. It is not a random gradient animation. It is a physics-based inverse rendering where we are optimizing a texture. It gives us the intuition that we can reuse samples in inverse rendering like we do in real-time rendering. Starting from here, in this project, we not only reuse samples in forward pass in inverse rendering, but also in light sample in differentiable rendering, edge sampling, and anesthetic sampling. After doing all this, we achieve up to 20 times better in parameter error in inverse rendering. Interested in how we do it, please come to our talk tomorrow afternoon. Thank you.
The reconstruction and decomposition of large-scale outdoor scenes is a difficult task. The complex lighting and shadow in these scenes make previous work struggle to produce high-quality results. To solve this problem, we propose SOL-NERF. SOL-NERF utilizes a novel light representation and multiple priors to implement high-fidelity outdoor scene decomposition. It can produce realistic rendering of scenes according to the applied lighting conditions. SOL-NERF can also faithfully reconstruct fine-grained geometry. If you are interested, please come to our talk. Thank you.
Thank you. See you tomorrow.
So diffusion curve is a primitive that smoothly interpolates color data in vector graphics. So previous numerical method incorporated finite element method, boundary element method, or boundary integration method, and each had their own issues. Our proposed method enables accurate computation of diffusion curves that remains faithful with even extreme zoom in. This could enable resolution-independent representation of images that can express small objects with their sharp features preserved, like this snail in a forest. Or we can also express high details of pupil while preserving crisp edge of eyebrow. Thank you.
We present the learning-based indoor lighting estimation method, which predicts spatially consistent HDR event maps from a single RGBD image. Moreover, it can take an RGBD video and progressively improve lighting prediction without flickering artifacts. Our method enables realistic object insertion with shadows, highlights, and reflection changing consistently as the sphere moves around the room. With video inputs, it can smoothly refine our lighting prediction as shown in the reflection on the mirror sphere. Thanks for listening, and please come to our talk for more details.
We propose a novel approach for photorealistic single-image novel view synthesis. The existing approaches are unable to handle view-dependent highlights, producing results with highlights that appear to be glued to the surfaces. Based on the image formation process, we propose to break down the view synthesis process into two subtasks of reshading, where the highlights are handled, and relocation, where the reshaded images are projected to the novel camera position. Our approach produces photorealistic results on a variety of real images. To hear more about our work, please come to our talk on Wednesday.
Thank you.
Compositing virtual objects into images found in the wild can be very challenging to do without the help of an artist. Using state-of-the-art approximation methods, results can look plausible almost automatically, but fail to account for shadow interactions. Specifically, the resulting color of virtual shadows often stands out when placed near real shadows. And if those shadows overlap, it can create overly dark double shadow artifacts. Last but not least, real shadows are also not cast in virtual elements when rendering. We propose a deep generative pipeline that handles these problems in 3 steps. First, we detect shadows on the ground with a high level of detail and estimate how soft those shadows are at each pixel. Using this information, we adjust the virtual shadows on the ground and then recast the detected shadows on the virtual objects. Read the paper to find out the details.
Or just come to our talk.
I love sharp images, but when I zoom in, my path-traced images often look pixelated. What if there was a new way to store them? One where you could zoom all the way in, and further in, and further in. The edges look sharp at all zoom scales, no matter how far you zoom in. What if it could also support curved edges and denoise your noisy Multicolor data too? What if it could also preserve sharp edges in your PD solutions? Stop asking what if and come find out how at our talk on discontinuity-aware 2D neural fields happening tomorrow afternoon.
NeRF is becoming a modern medium for 3D contents. How to recreate and remix objects from existing models remains a problem. Like here, we want to stitch the arms of a right model to left one. How can we do it? We present the seamless NeRF, which performs appearance blending in the gradient domain, inspired by Poisson image editing for 2D graphics. See, the textures and appearance are harmonized. And we showcase more results in this page. For more details of our method and results, please come to our talk. Thank you.
Solving PDEs without discretization is valuable in many graphics applications. Monte Carlo PDE solvers are unbiased but suffer from high variance. In contrast, neural fields-based solvers offer faster inference but often yield biased outcomes. We propose to use neural field caches to reduce the variance in Monte Carlo PDE solvers. Our method excels when computing is limited and enables effective bias and variance trade-offs. Please come to our talks for more information. Thank you.
The most important constants in our universe are 4. P, also known as pi, for the circle. Phi, the golden ratio. Maybe many of you know it. E, Euler's constant. And Z, this is our constant. This is a magical constant that converts the generation of low discrepancy sequence into multiplication. So come to our talk tomorrow to see.
Light pollution is the presence of artificial lighting causing negative effects on the beauty of the night sky, making us hard to see the beautiful stars as shown in the background of this slide. Our goal is fast rendering of sky glow caused by the city light sources. The challenge is the long computation of light scattering due to numerous light sources. For every point on every viewing ray, we have to accumulate the intensity of scattered light by many light sources. We propose a super-fast method, thousands times faster rendering speed, and we developed a forward and inverse investigation tool for light pollution. Come to our talk.
Head-mounted displays work by rendering perspective-correct images consistent with a user's real eye location. Inconsistent render and viewing geometry is problematic in head-mounted displays because dynamic errors from user motion make inaccuracies more obvious. Very few studies have explicitly examined how accurately render cameras need to be positioned, and all of them that have been run have been looking at stationary observers. We introduce hardware to enable user study that examines this question explicitly and determine requirements for active observers across a variety of viewing conditions in augmented and virtual reality.
The human eye's adeptness at analyzing visual features located at the center of our vision comes at the cost of us having poor peripheral vision. Therefore, we've evolved to rapidly shift our gaze towards objects of interest in our periphery to fully understand the environment we're in. Unfortunately, some gaze movements which change the depth of the gaze point, as shown in this video, take longer than movements without. In this work, we study and map the relationship between gaze point displacements in 3D and the delay of gaze movement completion. Please come to our talk to learn more about which eye movements are fastest, which ones are slowest, and how this work can be leveraged for VR and AR applications.
Thank you.
Contrast and brightness play a key role in enhancing visual quality, with high dynamic range content becoming more and more popular. However, SDR displays may not be capable of adequately representing HDR content. Therefore, tone mapping operators are required to map HDR content to a display's capabilities. However, for control, tone mappers often rely on outdated heuristics or manual input, which may not correspond to the realities of human perception and novel display modalities like virtual reality. Our perceptually adaptive tone mapping framework automatically selects a curve that optimally represents the content for the target display, running in under 1 millisecond on a Quest 2 headset. If you want to know more, see you at our talk.
Thank you.
Have you ever been in a hurry to record a dataset for your next big NERF paper that is due tomorrow? We know this may involve many time-consuming steps. And then you realize something got messed up on the way. Now you start panicking because you know you have to go through all of this again. But can this process be more interactive? With our method LiveNBS, you get a high-quality preview already during capturing. LiveNBS got you covered for the next dataset, and your paper will be ready in time, even if the deadline isn't postponed. See you during the talk.
Imagine taking a bunch of photographs of a scene, and together with a point cloud, we can create great novel views and fly-throughs. In this case here, of the famous Melbourne American Football Stadium. But what if the point cloud is less accurate? Then the resulting rendering exhibits error and is lacking detail. We will present a solution in creating an error volume of visual error and add additional points based on that volume. This allows us to render with great quality and in real time. If you want to know why and how we use computer tomography for that, come to our talk. Thank you.
In everyday photography, single captures often lead to defocus, blur, and overexposure. We aim to improve visual experiences by exploring all-in-focus HDR images. Traditional methods require labor-intensive serial operations, involving extensive image capturing for different exposures and depths of field. They then use multiple exposure and focus fusion, which is inconvenient. We propose a novel method that reconstructs all-in-focus HDR images from sparse inputs, offering promising results. Additionally, our approach supports post-editing, like refocus and exposure adjustments. Join our talk to see it in action.
Thanks.
We present multiple bounce Smith microfacet BRDF using the invariance principle. Follow the previous work, microfacet model is equivalent to a semi-infinite homogeneous medium. The invariance principle is based on a simple but effective observation that adding a slice of media doesn't change its reflectivity. So the total contribution of the added layer must be 0. Then we can derive the multiple bounce BRDF. Using invariance principle leads to a simpler derivation and a simpler formulation. Come to our talk for more details.
We introduced a new BSDF model for the rendering of porous layers, as found on surfaces covered by dust, rust, or spray paint. Our approach is based on a distribution of microscopic opaque ellipsoids that we call micrograins that are scattered over a base surface. By increasing the number of micrograins, we can increase the filling factor of our porous layer. We use distance field statistics to derive the corresponding normal distribution function and geometric attenuation factor, as well as the light view dependent field factor to blend between the porous and base layers. We can obtain with our model a variety of visual effects, such as hazy reflection, grazing angle color changes, dotted surfaces, and some more. Thanks.
Daily life objects can be modeled as layered. They exhibit diverse appearances due to variations in their volumetric scattering. However, the light can be reflected many times inside, making it hard to evaluate subsurface light transport. Recently, we have observed the transformative potential of implicit representation. But this time, we employ a pair of networks to reference the concept of meta-learning. It combines BSDF net to encode materials and meta-net to map physical parameters to neural weights. Our approach also applies to the spatially varying case, providing convenient material editing and better generalization.
G'day folks! Have you ever wondered why 3D speech-driven avatars don't feel alive? That's because they're all hat and no cattle, mate.
Exactly. Most methods focus only on the lip sync, but they completely ignore emotion.
True blue, mate. It's a tricky challenge, right?
Right. You see, trying to edit your lip sync or your emotion could actually break the lip sync.
Oi! There's nothing wrong with me lip sync.
That's right. That's thanks to our content emotion disentanglement mechanism. We can edit your emotion freely.
That's a fair dinkum achievement, I reckon.
Come to our talk.
Neural radiance field is not relightable in a straightforward way. We present a new method for high-quality view synthesis and relighting called LitNerve. LitNerve performs an intrinsic decomposition of a radiance field into albedo, direct light transport, specular, and indirect components. Putting them together, we get a full rendering. The method can be re-rendered with directional lights and even near-field light source. Come to our session on Wednesday afternoon.
Eiffel Tower is a one-of-a-kind capture rig with up to 22 cameras pointed inside out that enables depth coverage and high-dynamic range captures. The goal of VR-Nerve is to bring high-fidelity workable spaces into real-time VR. The demo shows a user with a Quest 2 VR headset exploring a virtualized space that is rendered live on a rendering workstation. The scene is fully workable in VR, so the user can fully explore the scene, walking and looking around freely. Here are more fly-through results of our scenes with automatic exposure adjustment. We took a system approach and introduced a series of techniques to achieve our goal. Please come to our session for more details.
In our work, we investigate current evaluation metrics for text-to-motion generation, attempting to identify which metric best aligns with human quality judgments. To do so, we collect a dataset of motion description pairs generated through multiple recent text-to-motion models and rated by annotators for distinct quality definitions. Our findings reveal useful insights about current evaluation metrics, including an overall lack of performance for single sample reliability. We also propose a novel learned metric which manages to significantly exceed all alternative metrics. Join our talk on Wednesday.
New game release coming out. I'm ready. Here are the character assets. 1, 2, 3. This many? How can I make the skeletons all compatible? We target or make 100 controllers? Same to rescue.
We present skeleton agnostic motion embedding where we project different skeleton motions into unified same space. With same, we can perform character animation agnostic to the character. For example, we can do motion matching directly in same space and morph the characters on the fly. And it's not only about motion matching, but it's a general framework. If you're interested in the next game changer in character animation, please come to our talk on Wednesday.
Excuse me, Sensei. I was wondering if you could teach me sword skills. But...
What bothers you, young Spot?
Sensei, we look very different. I don't know how to transfer your motions to mine.
Don't worry, young Spot. I will use a Gon's-based jutsu that automatically learns to transfer my motion to your body.
Wow, can't wait to see.
Adversarial correspondence embedding jutsu.
We present the first reinforcement learning-based approach that explicitly models full-body visual character fatigue as shown here. The character discovers unseen rest and fatigued motions without actually seeing different levels of fatigue during training, nor requiring any muscle simulation. For this, we propose a two-step learning approach. First, we leverage imitation learning to train an expert policy to perform the given task. Second, we learn a fatigue policy by limiting the torque bounds based on the three-compartment controller model from biomechanics literature. Our method enables the automatic emergence of realistic rest and recovery behaviors and motion variations. And if you're not too tired or fatigued, please join our talk on Wednesday evening. Thank you.